So what's going to happen is we're going to create these solid figures. We're going to find the volume, and the cross sections are sort of the slivers that make up the figure. The best analogy I can give you that to me makes a lot of sense is when you think of a ream of paper, right? It seems like a solid, even though it's made up of really thin layers of paper, right? And as you add more paper, the sort of thicker the solid gets. That's kind of what a cross section is. Think of each cross section as like a piece of paper in a ream of paper. The thing that will happen is that the cross sections will not always be rectangles like in a ream of paper. They will be other shapes. And so what's important is that you have to know the volume, you have to find the area of each of those shapes, and then essentially what we're going to do is integrate from one limit to another, sort of like a Riemann sum when we added up all the skinny rectangles, and then we got the total area. It's the same idea. We're adding up the areas of all these little shapes, and that's going to give us the volume. So on page 185, there's a list of formulas. If you want to screenshot it from there, you can. If you want to write them down, great. If you just know some of these, great. But these are the things, the main ones that are going to come up. Of course, the area of a square, if our cross sections are squares, it's just the side squared. If I have a rectangle, base times height. Semicircle, so half of a circle, meaning you'll have a flat side, and so the area of a circle is pi r squared, and then of course semicircle is half of that. Triangle, half times base times height. The equilateral triangle is one that's sort of useful to keep in your head. This would be one to memorize. The area is the square root of 3 over 4 times the side squared, okay? Because the base and the height end up being basically the same. But we have this square root of 3 over 2 multiplier, right? So in other words, we have a side, and then the height of the equilateral triangle is the square root of 3 over 2s, right? And that's because the height is constructed by using a 30, 60, 90, and then you have the 1/2 that's already there. So that's where this formula comes from. This will be useful at some point. Could show up in an FRQ, okay? Now, the two formulas, they're really the same formula, but it depends on if we're perpendicular to the x-axis or perpendicular to the y-axis, okay? So on this top one, perpendicular to the x-axis, so all of the shapes, whichever shape we're talking about, the areas are going to be perpendicular to the x-axis. And so we're going to integrate from a to b, whatever those limits are, with respect to dx. If it's perpendicular to the y-axis, it's just with respect to dy. And I think I have an example of each in this today. Again, all of this is on that page 185, I think it was 85. I'm sorry?
I think the thing that we just did was on
186, okay. All right, let's just get into some examples because I want to show off my drawing skills, and even though this first one is now, when I think about it more and more and more, I want to fix it, but I'm not going to fix it today. Maybe for next year I'll fix it. But here's example 1, okay? And they've given us part of it. All right, find the volume of a solid whose base is a triangle bounded by the line y equals negative 2x plus 2, that's this line right here. X equals 0, that's the y-axis, and y equals 0, that's the x-axis. So basically, this triangle here is the base. The cross sections are squares. Okay, so I've got a bunch of squares. And the thing that's interesting is the squares are going to change shape since they're perpendicular to the x-axis. So the first square is going to be 2 by 2. Okay, and then as we move inward, the squares get smaller and smaller and smaller and smaller until eventually we have the smallest possible square. at the end, because this is the length of the side, all right? And so they went ahead and set it up for us already. They told us it's from 0 to 1, and we'll talk about these limits of integration a little bit more, okay? Now, here's where my now bad drawing comes in, and I'll explain why I think it's a bad drawing in a second. But I honestly think whenever you do these kinds of problems, you should practice trying to draw what you're looking at, okay? And so what I've done is I'm going to take this and give it a tilt, and that's kind of what so this darker green is the base. Why I don't like this is obviously this is not a square. This looks like a rectangle. I wish I would have made this taller, and that would have looked more like a square. But at the end of the day, my hope is that you get the point. I'm going to extend it anyway because I can't help myself. It definitely takes practice. I did not do it on the first try. So that looks more squarish, doesn't it? So if that's kind of the backside, right? And of course this front would have to be taller too. And okay, closer. I know that now it just looks messy, so I'm going to get rid of all that. Oops. I would have, if I were to do this again, which maybe one day I'll do it again, I will make it look more squarish over here, because as we talked about, this distance is 2, so from here to here is 2, which means here to here should also be 2. All right. But look, we don't need to get hung up in that as much as I can't help myself. It's not that important in order to solve this problem, okay? And so what I'm going to do, we're going to look at one little square that this particular, okay? And so right here, one of the ways that I've seen it labeled, and I think it's a good idea to label it, is particular square is thought of as dx, okay? That's the change in x. And the skinnier the square, of course, and the more squares we have, I mean, let's be real. There's an infinite number of squares that I can put in there, and that when I smush them together, create a solid, okay? And that's just the bottom of the square. So what I like to do is try to fit a square inside of my figure, right? So there's going to be a square as far as I can go going backwards, a square as far as I can go going forwards. And they're going to get skinnier and skinnier and skinnier, and that is this dx, okay? And so this is the square that I've drawn on the inside, okay? I'm going to do one more just so you get the reference, okay? I'm going to put another square in. It's going to be bigger because I don't have a lot of room to put one in the front. So again, I know it looks rectangular, but you see the match up here. This would be the base of the square. There's another square on the inside, and I would have a bunch of them. Now, I am not suggesting that you have to create more than one square. If one square is enough for you to figure out what your formula is going to be that goes into your integral, that's totally fine, okay? I thought for this first one I'd draw a little bit more because, again, the better you can see it, the easier these problems get. Questions so far? All right. So now what we have to do is figure out what are the actual lengths of those sides of the square, okay? And the best way to look at that is to look at these here, okay? This length, since it goes from the x-axis to this line, this y value, all the y values along this line, this red one, this purple one, are defined by this equation, y equals. So at this point, y equals negative 2x plus 2. At this point, y equals negative 2x plus 2. And as x gets bigger in this problem, y gets smaller. So as x gets bigger, y gets smaller. As x gets smaller, y gets bigger. So this formula is what ends up being the length of one side. Well, if this is the bottom, okay, and it's a square, then both sides are the same length, okay? That length is negative 2x plus 2. And so I have a square with all the sides being defined by that y, okay? So far, so good? All right. Now I need to just put it into our integral formula, okay? And some of these will say set up, some of them will say find the volume. They'll say find the volume. So all I've got to do then is plug that in, okay? They already gave us that it was from 0 to 1, okay? And we could figure that out. And then since it's side squared, I take the side, plug it in, and now we actually have to figure this out. So I want you to actually figure this out. Go. What's going to be required here? What are you going to have to do in order to integrate this? U substitution. Very good. Yeah, I guess I didn't think about that. If you want to multiply that out first, then you wouldn't have to do U substitution. So what you're going to see up here is U substitution. But yeah, if you did multiply that out, you wouldn't have to. That's probably easier now that you say that. All right, so again, I didn't even think of multiplying this out, so I did use U substitution, and then I got rid of the pictures because I need some room over here. So making U negative 2x plus 2, du is negative 2x, got negative 2 dx, then get the dx, isolate the dx. Here's where I at. And then don't forget to change the limits of integration, right? Plug 0 in, I get 2, plug 1 in, I get 0. So even though this looks backwards, right, this is going to give me a negative in all likelihood. I already have a negative out here, so we should be good. Okay? And I'm sorry? You do not. Because we did use substitution, you just have to leave them. You plug these in and leave them in whatever order they're in. And again, like I said, this ends up giving me a negative, but I already have a negative. Of course, we're finding volume. So again, with volume, we're looking at cubic units. They didn't give us it, so you should probably put it, if you did make it 1.333 units, cubic units, that would be fine too, okay? So that's the first one. Questions about that? And you would have gotten the same thing had you just multiplied this out and not used U substitution and went 1 to 0, okay? All right, next one. Same base, but different cross sections, okay? So this, now again, this one says set up, but do not integrate. So we're not actually gonna find the volume. Solid, same base. Cross sections now are semicircles, still perpendicular to the x-axis, okay? So again, I went ahead and drew a little drawing. I just put one semicircle in there for now, all right? But the thing is there's gonna be a bunch of them. There's gonna be one starting at the back, and it's gonna work its way forward. The trick here is, since we're finding the area of a semicircle, we only need the radius. This dimension, as we already learned, was negative 2x plus 2, but this is not the radius. This is the diameter. So I'm going to need half of that. But before we get there, I want to show you my drawing. I'm pretty happy with my drawing. Okay, so this is the semicircle we're talking about. And this shape is going to look like this. It's kind of cool, huh? Originally, when I did this problem, I fit semicircles inside of that rectangular prism that I created. Or triangular prism, not rectangular, triangular prism. Prisms are named by their base. Did you know that? Okay. So it's sort of like a domey cone. It seems like something you'd see on Star Wars. And granted, I just listened to a podcast with Mark Hamill in it, so maybe I have Star Wars on the brain. But doesn't it kind of? Yeah. There's some Star Wars-y features to it. Like their spaceships kind of looked like that a little bit. There was some of that. Yeah, I don't know. I think it's the lines when you had to fly through the little. I don't know. It's whatever. Lasers. All right. So, since the area of this semicircle is 1/2 pi r squared. Okay, this is the area. I should write that in. This is the area. as I mentioned before, this is the diameter. So I need to find the radius. Well, we know that this diameter is negative 2x plus 2, so I just need half of that. Right. So my radius is half of negative 2x plus 2. And I'm going to distribute that and make it a little simpler. Okay, so I get negative x plus 1. So the radius of that semicircle, of all the semicircles, is negative x plus 1. So then from there, we have everything we need. Okay, we're still integrating from 0 to 1. I'm using this formula. Okay, now you could put the 1/2 pi inside the integral, or you can put it out because all of this is a constant. But it doesn't matter. I put it in, and then here's my formula. Okay. From 0 to 1, 1/2 pi. This is the radius squared. Don't forget your dx. And then we would simplify that if we want, if it asks us to actually find the volume, but it does not. So we're good. I would say, if you were asked to find it, I would put the 1/2 pi out front, integrate the variable expression, and then just multiply it by 1/2 pi at the end. Okay? Example number 2. So far, so good? All right, let's keep moving, because we got a lot to get to, because now it's going to get a little trickier. All right, again, set up but do not integrate. This is example 3. So these are all in your book. An integral for the volume of a solid whose base is bounded by. Translation, it's an irregular base. But the cross sections are rectangles. And the heights of these rectangles are 1/4 perpendicular to the x-axis. Okay, they're telling you the height is 1/4. What they aren't telling you is the base. Okay. I'm not familiar with that song, and I'm glad I can't hear the projection from where you're sitting. All right, now what I would do, if I were you, I would graph these lines, okay? So make an attempt at graphing those, please, and then we'll talk about how to go from there. Because until we graph that, we can't see the base. Do that, please. Now, if this was a calculator active problem, you could actually put the graph in your calculator, but I would like you to do it by hand for today. It just needs to be a sketch, nothing special. Here's my graph, okay? So here's my line y equals x. This is a parabola opening down. It's a standard parabola, it's just moved up 2, right? And so it doesn't have to be perfect, because what we really have to do is, there's a couple things here, right? First off, my shaded region, the base of this solid is where the lines intersect, right? So we're talking about this right in here is my base. Okay. Because it says that the base is bounded by. Okay, and so that means the intersection of this equation and this equation. Okay. And of course, these points are going to be important for us as well, because those will be our limits of integration, but we're not there yet, okay? Again, we're perpendicular to the x-axis when we have rectangles. This rectangle is not as, I didn't make a solid out of this. I tried to sort of draw a rectangle coming at you. Okay, so picture this rectangle coming out of the screen towards you, okay? And again, for me, I like to then draw it in 2 dimensions. So we know what we're actually trying to find the area of, right? Because ultimately, what we're going to do is we're going to add up, using integration, the infinitely small width rectangles that are going to fit in here, okay? They told us that the height was 1/2. What I have to be able to figure out is what is this base? What is this length right here? So how would I find this?
Just negative x squared plus 2 minus I.
It is, very good. So this y minus this y. Since this y is bigger than this y, you just subtract them and that tells you the vertical distance. And so that is just negative x squared plus 2 minus x. So now we have everything we need, almost. Okay? Something we've talked about before and I will re-emphasize, never trust the picture. Okay? In order to get my limits of integration, I still need to know these 2 points of intersection. Okay? If I have those points of intersection, this x value here, this x value here, then I know what goes in my integral. Okay? So, of course, the way to do that is to solve a system. Okay? And so that means set this equal to this, because I can just use substitution. All right, so negative x squared plus 2 equals x. And they definitely are going to want to see this on the AP exam. They're definitely going to want to know where your limits of integration came from. So this is an important piece to show. I'm a big fan of always having my x squared be positive, so I'm going to move these two to the other side. And so I get x squared plus x minus 2, factor that out, x plus 2x minus 1, which means x is negative 2 and 1. So those are going to be my limits of integration. So this is x equals negative 2. This is x equals 1. And now I have everything I need. Okay? I'm going to be multiplying the base times the height. I have my limits of integration. So my setup is simple enough. Negative 2 to 1, 1/4 times that. I'm done. Something that some of you guys did yesterday on the quiz that I really want to discourage you from doing is simplifying. When you have a question that just says set up, don't do anything more than this, okay? Don't try to I realize we did some factoring down here. This is kind of a different thing, but just leave it like this. This is fine, okay? If it asks for the actual answer, then yeah, keep going with it. But in this case, obviously there's nothing to combine anyway. But I would discourage you from going further. One of the things that I've seen in the past is the algebra mistakes get you in trouble and then you lose a point on an FRQ that you would not have lost had you just stopped right here and left it. Okay? Questions on that? All right, let's make this a little tougher. I feel like this is too easy for you right now. Is it? It's review. Okay. One more example. We'll do example 4. Now we're going to be perpendicular to the y-axis. Actually, there's 2 parts to this question. There's part A. I think I'd also do part B in a minute. Yes, so we're going to do part A and part B. So this time we have a circle as the base. We have equilateral triangles perpendicular to the y-axis. Since they are equilateral triangles and our base is a circle, what shape is the solid? What kind of cone? It is definitely not a cylinder. Cone is correct, but can you be more specific?
Is it like the, wait, are there different cones?
No, it is not an equilateral cone. It's called a right cone because it's a right cone because the height of the cone, since we have equilateral triangles, will form a right angle with the base.
That's pretty close.
Yeah. Okay. All right. Again, this time I'm not going to try to draw a cone. What I'm going to try to do is talk about the cross section. So since it's perpendicular to the y-axis, that is going to be the base of the equilateral triangle. So if you want to sort of picture an equilateral triangle coming out of the screen at you, that's what's happening. And of course, the wider the base, the taller the cone. The skinnier the base as we approach this side, the shorter the cone. Okay, the shorter the triangle. And so in the middle here is where my peak of the cone is going to happen. Okay, because that's where the distance is the longest. All right, so this is where it's important to, again, have that formula for the area of a equilateral triangle in the back of your head. In order to find one side of this equilateral triangle, what we have to do is figure out what this length is, all right? And here's how this is going to work. Our dilemma is here, this side, and I'm going to highlight it, is x. Okay, that's it. Just from 0 to x, that distance is x. Well, that's only half of the base, so I need to have two of them. Okay, and that's where I'll have my base of the equilateral triangle. The problem is my equation is not in terms of x. I do not have x by itself. I have an x and a y. So unlike the other problem where we got y by itself, what we're going to have to do is get x by itself. So again, the base of this equilateral triangle is going to be 2x, two x's, but I don't know what x is. So please get x by itself here. Go. All right, so technically, yes, when you get x by itself, it's plus or minus, right? If you didn't have the minus, you'd only have a semicircle, right? So if we're talking about the positive side of x and the negative side of x, so technically, yes, you need the plus or minus. However, in our formula, we're saying my positive x here, I'm just going to take two of them because we are talking about distance, right? So the actual base of the equilateral triangle is 2x. In other words, multiply this by 2, and now we can just disregard the plus or minus because now I get my length. This is the base of the equilateral triangle, right? 2 x's. This is what we're going to use in our formula. Well, in our formula, this is one side, right? And again, we're not solving it, we're just setting it up. Now, what are my limits of integration going to be? Since I'm moving this way, what is the highest y and the lowest y? Negative 1 and 1, and we know that because the radius is 1. Okay, so setup is going to, again, here's our formula for the area of an equilateral triangle. Square root 3 over 4 s squared, and so my setup just looks like that. From negative 1 to 1, got to have the square root of 3 over 4. Take that side that we generated here, square it. This is with respect to y.
And then we were to solve it, take the square root of 3 over 4 on the outside.
I would take action, yeah, because this is being squared. Yeah, that's 4, so that's just square root of 3 on the outside. But you could, yeah, I mean, it doesn't, you could just throw this out here, integrate that. The squaring and square rooting is going to cancel, and then the integration really is not that difficult. All right, let's look at part B for that problem. Part B says rectangles. Again, we're still perpendicular to the y-axis. So the only thing that's going to change is the formula that we use, okay? Rectangles whose heights are 3 times their bases and whose bases are perpendicular to the y-axis. So we're still talking about x, right? This is still going to be, our x is still going to be this. Well, we already found out what that x was, okay? That's the base of that rectangle. The height is 3 times that base. And so again, we know that x is this, or the base of the rectangle is this, because we figured that out before. The height is going to be 3 times that. So here's my base, here's my height, I just multiplied it by 3, base times height. Again, like I've been saying, don't simplify it. Just set it up. I really need an extra set of parentheses there, don't I? There we go. Okay? And just call it good. If it asked you to figure it out, then fine. You could do that pretty easily. But those are the different kinds of cases that you're going to run into today. On Monday, we're going to talk about solids formed by rotating around an axis or another point. So the discs and washers will be Monday, okay? And hopefully another shot at that from last year will make it easier for you this year.